Hey class, this is 9.6, 9.7. I'm going to stop short from 9.8 because there's some stuff in there that gets pretty confusing. There's some pictures that are pretty confusing that we're not going to spend a lot of time on in class. So I just stopped at 9.6 and 9.7. So let's take a look at this. Valence bond theory is hybridization is a major player in the approach to bonding. Of course it is, because that's how it all works. There are two ways orbitals can overlap to form bonds between atoms, and we're going to talk about those two different ways. So we take a look. Once I explain the two different ways on how the orbitals can overlap, it'll be hopefully, it'll be pretty obvious. So the first way that we have an overlapping is head-to-head overlap, which is just like you see at the pictures here. So I'm going to move over here and get closer to the board so you can see this. So we are overlapping like face-to-face, like the part of the p orbitals that I see here for hydrogen and chloride or chlorine. Notice that it overlaps like face-to-face. This part right here is overlapping face-to-face. And it's not like where end-to-end is really what I mean. There's the overlap end-to-end from chlorine to chlorine. So of course, there are other p orbitals for chlorine because chlorine has 5, so 2 out of the 3 p orbitals are filled. So you have one that looks like this and one that goes like this way, but it's the end-to-end one that, so here, let me explain what's going on here. So the cylindrical symmetry of the electron density about the internuclear axis. So the internuclear axis is the axis that the nucleus is on. Notice that this part of I should use a different color. Notice that this part of my p orbital is overlapping with the s part right there. Notice that this part of my p orbital is overlapping with this part of my p orbital on the internuclear axis. Okay, so the overlap ends up right there. So that's end-to-end. So what else could it be? If it's a sigma bond, that means it's end-to-end overlapping, and people are confused by that. Now, okay, first of all, when does this happen? All single bonds are sigma bonds. Okay, all single bonds are sigma bonds. So if I take a look at something that looks like this, I have 4 overlapping bonds end-to-end, which is sigma. Okay? So what's the other choice? Like, what else could possibly happen? These are called pi bonds, literally pi. Okay? And notice that they are not, these two, this part here and this part here, are side by side. This is not end, oh boy, things getting creative, not end to end, okay, not end to end. This is side by side. That's what a pi bond is. So when I have a double bond between 2 carbons here, this carbon right here, carbon number 1 and carbon number 2, this first carbon has 3 sigma bonds, 1, 2, 3, and 1 pi bond, 1. Okay, so the first carbon here would have 3 sigma because the first bond, whether it's a single, double, or triple, is always sigma. And if it's a double bond, the second bond is always side by side or pi. And that's how you count them. So if I'm talking about the second carbon here, that would be 1, 2, oops, I screwed that up. Poop. Hang on. I can just erase it like this. There. So 1, 2, 3 sigma bonds. Okay, there's 3 there. And then this one here would of course be a pi bond for the second carbon. So that would be 1 pi. Okay? If I have a triple bond, carbon has a triple bond like this, and a single bond here, and a single bond here. How many sigma bonds and how many pi bonds would I have? Well, that's easy, because if it's a single bond like this, that would be a sigma. If it is a triple bond, 1 sigma and then 2 pi. So I have 2 sigma overall, and then I have 2 pi bonds here like that. And this one does the same. So I have single is a sigma, and then one of these is a sigma, and then the other 2 are going to be pi and pi, like that. So how do we get the side-by-side p shaped sublevels to bond, like those orbitals from this? Oh, let's take a look. 1 bond is a sigma bond. Here, this shows us 1 bond sigma plus 1 bond pi for a double bond, and then 1 bond sigma plus 2 bonds pi for a triple bond. So how does it work? Well, here, this right here is our end-to-end. Okay, that's our sigma right here. Here, I'll do a little sigma right there. And then I have a pi bond here. This is where, now, even though it's top and bottom, and that looks like it's 2 bonds, it's actually only 1 pi. So when you look at these pictures, you're going to be like, wait, what do you mean that's only 1 pi? Remember, a p has 2 lobes. It has 1 lobe on top and 1 lobe on the bottom. It's still the same orbital, though. So this right here and this right here are all part of the same orbital, or part of the same bonding system. So that right there, both of those are 1 pi. Now what happens if I add a second pi bond? So here we have our sigma. I'll do this like this. Here's our sigma bond because it's end-to-end or overlapping. One of the sides then would be, let's see if I can do this. That's 1, and that comes out to there, so that's 1. That goes to there and to here, so these are 1 pi, and then with the blue you can see the other ones like this and like that. So that would be 1 sigma and 2 pi, even though there are 4 lobes that are overlapping end to end. Okay, I know that gets confusing, but we're going to ask it, like if we take a look at this, how many sigma, how many pi bonds for a resonance structure? Should be the same, because it's just a placement of where the double bond is. So if I'm looking at this, there would be 1 sigma there, 1 sigma there, 1 sigma there. That would be triple. And then 1 pi. So, and that's the same for all of them. So that should not change. In reality, it says each of the 4 atoms in the nitrate has a p orbital. So the p orbital is on all 3 oxygens, overlap with a p orbital on the central nitrogen, as you see what's going on there. So, okay. This means that the pi electrons are not localized between the nitrogen and one of the oxygens, but rather delocalized through the whole ion. So, okay, so what does that even mean, delocalized? Notice the difference between the first picture and the second picture, the top picture and the bottom picture. Here they are not delocalized, here they are localized. As in, these electrons stay there, and then between this 2 bond here, they stay there. Okay, that would be what we saw like this, okay, with a double bond between this one and then over here would be the combination of all 3 resonance structures, where now the electrons are kind of gathered all up in there and all down below here. And that would be like when I have the nitrogen like this, I have 1, 2, 3. That's kind of a half bond, kind of a half bond, kind of a half bond to all the oxygens like this. Okay, that's where the delocalized comes in. That's kind of, you know, that's kind of iffy. That screws up people. I understand. Here's benzene. Benzene has these 2 resonance structures. We show the 0 or the circle on the inside to show that they're delocalized. What does that mean? Well, delocalized means that the top electrons, like all of the top ones here, kind of fit together, and all of the bottom ones there kind of here. There's a better picture, or at least there should be, of resonance and how delocalized. So let me just move up here so you can see them. There. The picture at the end here shows how the top electrons are delocalized and the bottom electrons are delocalized. The blue area in the middle is the internuclear axis, where all the nuclei are for that molecule. molecular orbitals. So, molecular orbitals. So take a look. I have a 1s and a 1s. Now, why does hydrogen come together to form with one like that and hydrogen, one like that? Why do these two come together to bond? Okay, the only reason why is because it would be a more stable configuration. Okay, so that means that some of the energy is given off, and hydrogen like this exists at a more stable state or a lower energy level than when you just have two hydrogens, like that. So this means more stable. This would only happen in nature if it were more stable and gave off energy. Okay, I simplified that, but that's basically true. So that means that we have a situation where, notice that I have hydrogen here, and they come together to form a bond, and that bond is lower in energy. That's why this kind of goes down like this. Unfortunately, now this is the part that's kind of strange, and I'm going to have to give myself a little bit of room here to show you what's going on. Unfortunately, those two electrons that fit into the 1s on the bottom, this would be the 1s bonding orbital here. That's all one orbital with two electrons in it, okay, just like we would expect. The problem is that we start off with a hydrogen here and a hydrogen here, and then one of the orbitals has to go up and the other orbital has to go down like this and like this. This one here is the bonding orbital, and when we fill this with electrons like that, like one electron there and one electron there, you know, it would work just a little bit better. My apologies here. I'm going to do this with a different color. So let me show you this one more time. Here's my hydrogen. There's the one electron for my hydrogen on the right-hand side. This orbital moves up, but there we go. But this electron moves down so that these two, a green and a blue electron, fit into an orbital of lower energy than they both were separate. And then I have the higher energy up here. This is called the anti-bonding orbital, something like that. Okay, so this down here is my sigma bond, end over end, of my S sublevel. And what I have is an electron from the left, an electron from the right come down here to the bonding orbital, and this one up here, this orbital up here in the blue is my anti-bonding orbital. So if I fill the bottom orbital but don't fill the top one, I have a stable bond, because the electrons are down into the stable region, like water flowing downhill. That's exactly what it's like. Okay, so those are molecular orbitals. So two hydrogens will create a bonding orbital, one bonding orbital, and a non-bonding orbital. And this non-bonding orbital is where this node shows up. Okay, this is the part that freaks people out. So a node is like an unstable region where electrons do not go. That's what this is here. When we have a node, that means that my two electrons are not happy together there. And if we have the same number of electrons on the bonding orbital, the one down here, as we do up here, then we don't have a stable bond, because these will cancel out the stability of those electrons. Okay, this is very advanced. Okay, this is very detailed as to why atoms actually bond together, using the easiest example here. So it only gets more complicated from here on out. So if waves interact destructively, the resulting orbital is higher in energy and an anti-bonding molecular orbital, which is what this is that I have circled up here. That's an anti-bonding orbital, and it has a node in it. Okay? So nodes, not good. Here's how they show them. Here's the 1s anti-bonding orbital. Here's the 1s bonding orbital. So I have a hydrogen on this side, on the left-hand side. I have a hydrogen on the right-hand side. They have electron, just one electron each. Those two electrons fall down here, here, into the lower energy, and no electrons go up here. This is why the hydrogen to the H2 bond works. So the 2 electrons going into the bonding molecular orbital, the bond order is half the difference between I don't know why they make this so complicated, is half the difference between the number of bonding and anti-bonding electrons. Okay, so I have 1/2 times the number of bonding electrons, which is 2, minus the anti-bonding electrons, which is 0, like this, which means that I have 2 times 1/2 equals 1 bond. Okay, 1 bond. So this right here is bonding. This one right here is anti-bonding. Sometimes we have anti-bonding electrons, and I'll show you how to handle that. Okay, so this is in the case of He2, the bond order would be 1/2. Now here are the 2 bonding, here are the 2 anti-bonding. So 2 minus 2 is 0, times 1/2 is 0. So there's no bonds that can form here. Okay, therefore He2 would not be something that happens in nature. So it does not exist, because these anti-bonding electrons in this anti-bonding orbital, okay, now that orbital just like breaks the bond up. So it does not happen. I'm just about finished here. You guys are hanging in there very good. So in case of He2, that is simply just not, it doesn't exist for reasons I still just explained. So atoms with both S and P, now we get into like some really messed up poop. So I'm going to stop there, and if we need to answer questions like this, I'll do that in class. And for my online class, you won't be answering questions about that. Excellent.